Banked curves. In this video, we'll be analysing uniform circular motion and the specific example of a car going around a banked track. So first, let's look at an example of a car on a normal road and the forces that are acting on it. So we have the mass of the car, and with gravity, we can consider the force in the downward direction being the car's weight. The force going forward, which is due to the car's engine and transfer of the energy through the wheels. The resistance force being drag or air resistance going in the opposite direction there. And the normal force of the car, which is perpendicular to the surface of the road. This force is from Newton's third law, being for every action there's an equal and opposite reaction. And if this force didn't exist, the car would travel through the road and sink into it, which wouldn't make sense. So now we've got an example of the same car, but now it's on a banked track, so an angled track. Okay, so let's look at the forces again. So we've got the force due to gravity and the weight of the car, still in a downwards direction. We've got the normal force here, which is perpendicular to the surface of the track. And then what we've done here is break down the normal force into its vertical and horizontal components. It's really easy to work with vertical and horizontal components in physics. There are a lot of tricks that we can use to make the calculations easier, and that's why we always choose the vertical and horizontal components. So being vertical and horizontal, they have a right-angled relationship and they're independent of each other. And what this allows us to do is when we have our vector diagram, we can use trigonometry and Pythagoras in our calculations. So using trigonometry, we can see that the horizontal force here is the normal force sine theta, and this is the vertical component of the normal force, and it's the normal force times cos theta. Using geometrical relationships in angles, the angle of the banked track is the same as the angle between the normal force and its vertical component. So this is theta in here. So when looking at a car on a banked track, the downward force due to gravity is given by the mass of the car times the acceleration due to gravity. And the horizontal component we can see is the force due to the centripetal acceleration of the car. So the centripetal acceleration of the car is v squared on r. And with Newton's second law, F equals ma, it would be the mass times A, and we receive this formula here. In this slide, we're just going to find a relationship between the angle of the banked track, the speed of the car, and the radius that it can turn in. Okay, so breaking it down, we found previously that the horizontal component of the normal force is given by the normal force sine theta, but this is also equal to the centripetal force, being mv squared on r. So we can equate the two values here. So going further, finding a relationship between the horizontal and vertical components of the normal force, we can see that tan theta is opposite over adjacent. So it's the normal force sine theta over the normal force cos theta. We can also replace the normal force cos theta, which is here, with mass times gravity, because looking at our force diagram, the vertical component of the normal force is here, and it's balanced out by the weight of the car here. So the magnitude of these two are equal, but in opposite directions. The reason why this works is because when the car is going around the track, it's not traveling up the track and it's not falling down the track. It's staying in that same location in the vertical direction. Now in this equation, what we're going to do is replace the normal force sine theta with mv squared on r, which will lead us to this point here. And with a bit of maths and cancelling out, we can see that tan theta is equal to the velocity of the car squared over its radius times gravity. So what this suggests is that for every angle of a banked track, there's a certain velocity that the car can go around at a certain radius without the requirement for the friction of the wheels to keep the car in track. This also means the car will naturally turn on a banked track without turning the steering wheel. And further from that, if you add the friction of the tyres, you can travel a lot faster around a radius when the track is banked. Alright, for this question, I'd like you to recreate the force diagram of a car on a banked track. So start with a banked track, draw your car on it, draw the main forces that you know, then break it down into its components.